Okay, so today we're going to take a look at section 3.1, okay, which is on what we call relations and functions. So I'm going to give you guys something to just take a look at first. And it shows different amounts of hours that Anne worked and how much money she made. Do you guys already have that printed on your guided notes? Okay. So she works as a lifeguard, and it says that she makes $7. So in 1 hour, she earned $7. If she worked 2 hours, she worked 14. 3 hours, she made 21. 4 hours, she made 28. So there's like 4 sets of numbers here. 1 hour resulted in 7. 2 resulted in 14. 3 gives you a 21, and 4 gives her 28. So pairs of numbers. What did we just say a couple minutes ago? If you have 2 numbers that you want to represent, you can use a what to represent 2 numbers with a comma between them? Yeah? A coordinate. So all this information could be represented as coordinates. 1 number, comma, another number. So let's take a look. So we could represent them as what we call ordered pairs. Do you guys already have that printed on your... No, you don't need that, but I think you have a spot now to write the ordered pairs. So let's do that. So you have a line that says S equals, and what was the first amount of hours that she worked? What did it say the first one was? Yep. 1, comma, and how much money did she make if she worked 1 hour? Yep. $7. So what we're basically doing is writing pairs of numbers where the first number represents hours, and the second number represents money. Hours, comma, money. Okay. Well, the next one was 2 hours. How much money did she make if she worked 2 hours? So 14. 2, comma, 14. Alex, how about if she worked 3 hours?
3, comma, 21.
3, comma, 21. And if she worked 4 hours, 4, comma, 28. So those are all called coordinates, or you can call them ordered pairs. And it's used to represent information. It's a lot shorter to write out 4 coordinates than it is to write out all these sentences of information. When you write a set of ordered pairs, that's called a relation. So on your guided notes, you have a blank after a set of ordered pairs, and you want to put the word relation. Think of relation, it's kind of like the word relationship. It's a connection between 2 things. This relation is a connection between how much time she works and how much money she makes. Time and money. That's the relation. Now, there's 8 different numbers in these coordinates. 1, 2, 3, and 4. And what do the 1, 2, 3, and 4 represent? Yep. In our word problem, those numbers are you are right, but yep, the hours. So those are the hours. These, the ones that I circled in blue, are money. All the ones circled in red are what we call the domain. There's a lot of different words for it. Domain is one of them. Input is another one. And I think you already have input on your guided notes. So when you write a set of coordinates, the first number in each coordinate is called the domain. So let's go back and look at our coordinates. And there are 4 numbers that are in our domain. Can somebody tell me the 4 numbers that are in the domain for that relation? Yep. 1, 2, 3, and 4. Yep. So the domain, okay, on your guided notes, the line that says domain equals, you just write down those 4 numbers. That's the domain. It's all the first numbers in each coordinate. Now, you might have a relation that does this sometimes. If you had something like that, and one of the numbers is repeated, you don't have to write it twice. I would say that the domain of these coordinates is 2 and 4. You don't have to write 2, 2, and 4. You just have to say 2 and 4. So you don't use repeats. Now, the second coordinates, okay, all the ones that I circled in blue, 7, 14, 21, and 28. Does anybody know what those are called? You can call them the domain. Yep. Those are called the range. Another word for range is output. So before before we started it back up, I gave you guys an example of an equation. And I said, if I plug in this number for x, what would I get for y? And Lexi told me. I think it was like, we plugged in the number 1, and we got the number 6. Well, the number that we plugged in, that's called the input. It's the number we put into a formula. When we do the math out, we got 6. 6 was called the output. It's the answer that you get when you plug something in. So let's look at our coordinates. What 4 numbers are in the range for that relation? Yep.
7, 14, 21, and 28.
Yes, 7, 14, 21, and 28. So on the line where it says range, right above example 1a, that's what you put in. Now, this one gave you the 4 coordinates, and it gave it to you as numbers. This problem is still giving you 4 coordinates. They're just not giving you the numbers. You have to look at the graph and figure the numbers out yourself. All right, so on example 1a, you've got the same graph I have. You've got the words domain and range off to the right. And let's see if we can figure out the domain and the range. To do it, we could just label each coordinate and we'll have the numbers. Yep. Yep. Can somebody tell me what this coordinate in the upper left is? Caleb?
1 to negative 1. 1 to negative 1. Wait. Or is it negative 1 to 1?
Negative 1, 1. Yeah. So it's left 1, up 1. Okay. How about that coordinate? Right where the 2 axes cross. Yep. That's 0, 0. Okay. How about the coordinate just down and to the right of the one by the origin? What's that one? Lexi? 1, comma, negative 1. And how about the one that's furthest down and to the right? Yeah?
2 and negative
2, comma, negative 2. So now this is just like the last one. I just want to know the domain and the range. Okay. What's my domain for those 4 coordinates? In other words, what are all the first numbers? If any repeat, you don't have to tell me that they repeat. I don't think we have to worry about that. Yep.
0, 1,
2. Yeah. Negative 1, 0, 1, and 2. Okay. That's the domain. And I like that you put it in order, lowest to highest. You're not wrong if you don't do that, but a lot of times when you write domain and range, you put it in order, low to high. Okay. And how about my range? How about Anaya? What's my range here?
-2, -1, 0, and 1.
Yeah, and she automatically put it in order from low to high. -2, -1, 0, and 1. It's just a list of all the second numbers in each coordinate. If you don't put it in order, you're not going to get it wrong. Okay? You can still get it right if you have these numbers in a different order. But you have to have those 4 numbers. Okay. Any question on that? So see, we're almost already done page 1. It's just that example took up a lot of space. Okay, so here's next one, example 1b. It says get the domain and the range of, and you guys need to write down the problem. And when you tell me the domain and range, if you can put it in order, that's great. If you can't, that's okay. It's more important that you get the numbers right than you put them in the correct order. Micah, do you think you could tell me my numbers that are in the domain?
2,
Okay.
0, -1.
Yeah, so he got all the numbers right, and as he said them, I just put them in order. -1, 0, 2, 3. Those are the numbers that are in the domain. How about the range? Anyone think? Yep, go ahead.
-2.
-2. Sometimes I check them off as I go, so I remember, especially if I have a lot of them.
0.
So we got 0,
1.
1, yep,
6.
6. Perfect. With 4 of them, it's not too bad, but if you had like 10 or 11 of them, you may want to just check them as you go, so you know which numbers you did or cross them out. Okay. Any questions on that? Okay. So if you look at both of our first examples, the first coordinate never repeated. Okay? The first coordinate or the first number in each coordinate never repeated. And when that happens, that's something special. We had a 2, a 0, a -1, and a 3. No repeats. The other example we did, -1, 0, 1, 2. No repeats. When you don't have any repeats in the first coordinate, that relation is something special. That's called a function. So on your guided notes, you guys have a blank spot, and it says when none of the first coordinates are the same, the relation is called a function. So a relation is just a bunch of ordered pairs, a bunch of coordinates. A function is a little bit more. It's a bunch of coordinates that never have the first number repeating. When I wrote this down, that's a relation because it's a bunch of ordered pairs. But it is not a function. Because if you look here, we have a 2. If we have a 2 as the first number somewhere else, then it's not a function. And we do. The number 2 repeated. Okay? Specifically, it has to repeat as the first number. I don't care about the second number. I don't care about the second number at all. But if the first number repeats, that is not what we call a function. Okay, so I think you guys have a bullet point right below that with a couple lines. And this is what I just said to you. In a function, which is again, that's just a bunch of ordered pairs, the second coordinates can be the same. That's okay. If the second coordinate repeats, we don't care. It's the first number in each coordinate that has to be unique. So like if I were to make ordered pairs of this class, like name, comma, age, one of these is definitely going to repeat a lot. If I wrote out coordinates with your name, comma, your age, and I did it for everybody in the class, which part of this do you think would repeat a lot? Guaranteed, you're going to get a lot of repeats in this part. Yep. The age, we're going to get a lot of repeats in the age. Okay? A lot of repeats. The name, well, not as many, but we would. There are people in here that have the same first name. So we have Abby and Abby. So if we were to make a list of all the names, comma, the ages, it would not be a function in this class because we have two people with the same first name. Everybody would have to have a different first name for it to be a function. And when you have two that are the same, it can lead to some confusion, just like when I call on somebody. So if I just said, Abby, how do we do the next part? They both would look at me because they don't know which one I'm talking about unless I look at them. So it's the same with numbers. If we have two that are the same, it can lead to some confusion, just like with names in a classroom. Okay, I think that's it for the first page. So if you flip over to page 2, example 2a at the top gives you a relation. Do you guys already have this relation written down? No? Okay, so copy down the coordinates where it says a equals. And now we're going to do what we just did before, but we're going to add one thing to it. I want to know the domain and the range, but I also want to know if this is a function. And A is just the name I'm giving to all these coordinates. I'm just calling these coordinates set A. You can give it any name you want. But I chose it. All right, so Tirza, when you look at that, can you tell me what my domain is?
1,
So we get 1. All right, I'm going to go over here now, -1. Okay?
2, -2.
So you got 2, -2. I won't cross them out because then you guys can't read them. Yep, keep going. And 3. So there's my domain. -2, -1, 1, 2, and 3. And Finnegan, how about my range?
-3,
Okay, so we got that one.
3,
3. Yeah, put that one over here.
5,
5. Okay.
negative 3 again.
So what should I do now?
Oh
What should I do now? Yep.
Negative 1.
What about the negative 3 he said again, though? Should I put it right here?
No,
Why?
because 1.
Yeah, 1's enough. We already have it. So we already have negative 3, so we don't need to worry about that one. And the last one Alex just said was negative 1. So this time there were only 4 numbers in the range, but there were 5 in the domain. So, is this a function? It's either a yes or a no. Whenever you have a different amount of numbers in the domain and the range, that's when you have to look at it a little bit carefully and see if it's a function or not. So what do we think? Is that a function or not a function, John?
Yeah.
It is a function. There was a repeat, but the repeat was in the second number of each coordinate. The first numbers were all different. 1, negative 1, 2, negative 2, and 3. Okay, those were all different. So the answer there is yes, that is a function. Any question on that? Okay, let's try another one, a little bit shorter. Okay, example 2b. So we have 3 coordinates. And they want us to do the same thing. Determine the domain, the range, and if it is a function. Okay, so on your guided notes, yeah, you guys already have a line, so we'll just fill it in. I didn't have a line on my notes. But what's the domain here? What's the domain of that relation, Dorian?
4.
Yep.
And then 6.
4 and 6. The domain is a list of all the numbers that are in the first coordinate, but don't put repeats. Okay, range. Okay, so what's my range? Yeah, if we put them in order, it's 1, 2, 3. Okay. We have a different amount of numbers in the domain and the range. That doesn't always mean it's something necessarily, but when it happens, it is a key. We should look at it a little closer. Again, that in and of itself doesn't necessarily mean anything. But using what I had said before, is this a function? Yeah? No. 4 and 4 is a repeat. It's like having 2 people with the same first name, and I just say the name, you don't know which one I'm talking about. If I said, look at the coordinate where the first one is a 4, well, you'd say, which one? They both are. There's 2 of them. Okay, so that is not a function. So no. Okay. Any question on that? All right, so I've given you guys relations a couple different ways. One way I gave them to you was as coordinates. Another way I gave them to you was as a picture. And you could figure out the coordinate from the picture. Well, here's a third way. This is a table. If the table is confusing, you could write it as coordinates. What this table really means is this. You could translate it to coordinates by putting the number that's in the x row first, and then put the number in the y row second. So this means -6, 13. The next one instead of writing it as a table, means -2, 12. Can somebody tell me what the third one would be? Yep. 4, 10. And how about the last one? What does that last column in the table tell me if I write it as a coordinate? Oh, Emily? 5, 9. Now, personally, would I do that? No, probably not. I would not take all the numbers in the table and rewrite them as coordinates. But if coordinates is what you're used to, and you like that better, then you can do it. Okay. This time, they're not asking for the domain or the range. All they want to know is it a function? So the answer here is either yes or no. Is this a function? What do you think? Please? Yes, how come? Which numbers? The first ones. And the first ones are called the inputs. They're also called the x's. None of the first numbers repeat. -6, -2, 4, 5. All different. So the answer here is yes. That is a function. Any question on that? Hey, this is another way that I can give you coordinates, and you have to figure out if it's a function. If you can't read the numbers that are in the bubbles, I don't think you guys have the numbers in your bubbles already, but it's a -7, a -1, a 4, and a 9. That's in the input. And then in the output, there's 5. -1, 1, 3, 5, 7. Now, I'm going to do the same thing with this one that we did with the table. I'm going to take this information and turn it into coordinates. Let's start with the first one. The circle on the left has all the x values. The circle on the right has all the y values. We have a -7, and it's pointing to a -1. So does anyone have a guess what the coordinate would be that represents that piece of information right there? Yep, here's it. -7, comma, -1. How about, now go to the next arrow. Brady, what do you think that arrow represents?
-1, -1.
-1, comma 1. Now, go to your third arrow. Yep, Michael? 4, 3. Go to your fourth arrow. What do you think that one represents? Yep. 4, 5. And Joe, what about this last arrow?
9 on the second.
Yeah, that's all that this chart is. So, determine if that is a function. What do you think this time? Is this a function? Yes or no? Kids? No, it's not. Why not? Because the 4 repeats. 4 is used with the 3, and 4 is used with the 5. That is a repeat. So the answer here is no. And this is a diagram. So this is a different way. We've got graphs, coordinates, tables, and diagrams. Those are really the 4 different ways that you'll see. Does anybody notice, if you look at this diagram, without making the coordinates, does anybody think they have a way they could explain when a diagram is not a function? Does anybody see what you might look for? Yeah?
The circle on the left is smaller than the one on the right.
So the fact that we have different amounts of numbers in each one, that can mean something. And you said that there were more numbers on the right than on the left?
Yeah.
Right. So basically what's happening here is if you look at the left, you have to match up every number on the left with every number on the right. Each one of them has to have a match. The problem is there's less numbers here than there are here to match up with. That means one of the numbers on the left is going to have to be used twice. So when you see an arrow coming out of the left side and going to two different numbers, then you know that is not a function. Yes? Yep. If it's confusing as a diagram, then just write it as coordinates every time. And you can always do it that way. Now, sometimes when we have a graph like this one, we want to know if it's a function, and we don't want to have to waste time listing out all of the coordinates. So there's a test that we can do. And the test involves making a vertical line and then dragging it through your picture. As you drag it through, as long as it only hits one point at a time, then it will be a function. Now, if you had something like this, let's add that one in up there. If you drag this vertical line through, yep, we're good. We only hit one. Whoop, not good. Now we hit two. If you hit two at the same time or more, then what that's going to mean is, look at the coordinate of this one. It's 1, 2. You have a 1 there. You have a 1 there. You just repeated the x value. So this idea of taking a vertical line and dragging it through your picture to see if it hits more than one dot at a time, that is called the vertical line test. So the vertical line test is used to figure out if something is a function. And it doesn't just have to be points that look like that. It can actually be a whole picture where all the dots are connected. Okay, so on your guided notes, you guys have two kind of bullet points there. So the first one, you want to put that the vertical line test is used to determine if a graph is a function. This test is specifically used when you have a picture. You don't use this when you have numbers. You use it when you have a picture. And the idea is when you drag the vertical line through your picture, it can only touch the graph in one spot at a time. If it touches it in two spots or more at a time, then it is not a function. So let's look at the graph in red. That's a pretty basic graph. It's just a line on a slant. And as I drag my vertical line through it, does it ever hit the red line in two spots at the same time? What do you think, Sean? No. It never hits the red line in more than one spot at a time. So this red line is a function. Let's try this one. This one curves a little bit, but as I drag it through it, does it ever hit the curve in more than one spot at a time? You can feel it? It does? So where?
Are we like this way kind of like horizontally?
No, vertical.
Wait. Oh, okay.
So does it? So what do you think? Alex?
At the ends.
Yeah, at the ends it looks a little steep, but I'll just fix the ends a little bit. It got a little steep there, but does it ever hit more than once? No. If you drag this through, it never hits the graph anywhere more than once, which means that this shape is a function. What are the coordinates for it? We don't know this time. We don't have coordinates. We have a shape. So that's how we can tell. How about the last one? So if I put it right there, it looks like it only hits once. Does that mean this is a function? You think, Brady?
No.
No, why not?
Because you're not flowing through it yet.
Yeah, I have to go all the way through. Not just does it hit it in one spot somewhere, does it only hit one spot everywhere? So if I keep going, how many times is the vertical line hitting it now? Yep. It's hitting it 3 times. That is not a function. So not a function. Yes, that is a function. No, that's not a function. Yes, I'm sorry, yes. Yes. So the vertical line test is used to figure out if a picture is a function when you don't have numbers that go with it. With a table, you'll always have numbers. And with a diagram like that, you'll always have numbers. All right, so we've got 2, I think, examples at the bottom of this page to look at, 3A and 3B. So let's look at it. Determine if the graph represents a function. So let's not list out coordinates here. I know we could here, but we're not going to be able to here because they're not dots. They're connected. So what's the name of the test that we can use to see if a picture is a function? Yeah? Yep, the vertical line test. So imagine making a vertical line and now drag it through your picture and check to see if it ever hits your picture in 2 spots at the same time. So what do we think about this first one? About Alyssa, what do you think? It is a function. So yes, it's a function. And can you tell me why? Right, it doesn't hit more than once on the vertical line. We would say that it passes the vertical line test. So that's what you could say. So explain this graph passes the, and instead of writing out vertical line test every time, I'm going to write vertical line test as VLT. You can write vertical line test if you want, but I'm just going to abbreviate it. Let's try this one. So I'm going to take my vertical line again. Do you guys already have this picture printed on your notes? Okay. So take your vertical line, drag it through, and you're focusing on the curve. And you want to see if it ever hits the line more than once. Okay. So as we dragged it through, did the vertical line ever touch the curve twice at the same time? Yep. No. So then this is a function. The answer is yes, because it passes the vertical line test. So it passes the vertical line test. It has to be a vertical line. It's got to be up and down. That's very important. Now, example 3C, I think that's on the last page of the guided notes. So let's look at that one. take my vertical line. That's a new one. All right. And do you guys have that one printed? The two curves that are kind of like pointing at each other? Okay. So let's drag the vertical line through it. Oop, I can stop right now. So what do we think? Is this a function? Yeah? No. This one's not a function. If we had numbers, we would say it's not a function because there is a repeat in the first coordinate. But we don't have numbers, so we do this instead. So this one does not pass the vertical line test. So explain, you could just say that it fails the vertical line test. So checking whether or not the first number has a repeat or checking if it passes the vertical line test is the same thing. It's just one of them is used with a picture, the other one is used with numbers. Any question on that one? Okay. So there's a little bit of a difference when we look at a graph that has dots versus when the dots are connected. When it's just dots, like on this, there were 4 dots. Each dot has its own x and its own y value. If we were to connect them, what we're saying now is we have a dot here, 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 here. We have a lot of dots. We have so many dots together now that they're all connected and it makes a solid line. So how many dots do you think there are from here, if I just keep putting them, up to there? How many dots do you think I could fit on that line? Yeah?
A lot.
A lot. How many do you think's a lot?
Well, depends on splitting the dots.
Let's make them extremely small. Like the size of the head of a pin. Even smaller than that, if you can imagine something smaller.
Yeah. Maybe
Thousands, more than that. Even more than millions. You can fit in as many as you want. You can fit an unlimited amount of dots between here and here if you make them smaller and smaller and smaller and smaller and smaller and smaller. So if I wanted to describe the domain and the range of this, I don't want to list out every single number, right? Because if there's millions and millions and millions and millions of dots, it's going to take a very long time to write them out as coordinates. So when they're connected, what we do is we start with the domain. That's left and right. So think of it like this. Imagine I put 2 dotted lines right there. This graph goes everywhere between those 2 dotted lines. The first dotted line is at -1. And the second dotted line is at 2. This graph will go through every single x value between -1 and +2. It'll go through 1.2, 1.3, 1.4, 1.57, 1.664. It's going to go through every single one of them. When it goes through that many, we can't list them all. So the way we would write the answer is like this. That's how you would describe the domain. That's an inequality from what we did last time. And this means that x is any number between -1 and +2. Because it's impossible to write them all. There's too many of them. So that's how we describe domain. And then for range, what letter in the coordinate is range usually connected with? Yep, the y coordinate. So range isn't left to right. Range is up to down. So you look at how high it goes, and you look at how low it goes. That's the limit, up to down, that this line goes through. The highest it ever goes is 1, and the lowest it ever goes is -2. So the way we would describe the range, we put the low value, we put the high value, and with range, we put the letter Y in the middle. And I'm going to do another example of this that's on your guided notes. And just like we learned, both inequalities point towards the smaller number. So this is saying that Y is any number, or Y means range, any number between -2 and +1. Why do we write it this way? There's too many numbers to list. As we said, there's millions, billions of numbers between -2 and +1. Think of all the decimals you can between those two numbers. So let's try another example. I think this one is on your guided notes. Let's start with the easy question first, which is this a function? So imagine dragging that vertical line through, and I'd like you to tell me if it would ever hit more than once. Think about that. If it doesn't hit more than once, we're good. It's a function. If it hits it twice, no good. Not a function. What do you think? Yeah?
No.
This is not a function?
Yes, it is.
It is a function? Why?
It doesn't touch more once.
It doesn't touch it more than once. Drag the line through. Perfect. Never touches more than once. Now, we have a picture that's connected. So, how many dots could you fit along that picture? What do you think? Yeah? Infinitely many. So you can't write the domain and the range by listing out every single number like it was just a couple dots. That's easy. If it's just 4 dots, we just write 4 coordinates. But we can't do it that way. There's too many. So let's start with the domain. Domain is which letter? Is that your X or your Y? Yeah? X. In which way does X go? Left and right? Or up and down?
Left hand.
Left and right. So to find the domain here, we want to figure out how far left and right this goes. Well, it goes that far to the left, and it goes that far to the right. And it hits every number in between, every decimal you can possibly think of between the left number and the right number. So, Mia, how far left does my graph go in this picture? I need a number. So that would mean that it stops right there. But I think it does go a little bit further to the left. -4. So this graph goes as far left as -4. And then it hits every number, -3, -3.2, -3.1, -2.44, -2.156, 0. How high does it go? It doesn't keep going to the right forever. It stops. Yeah? It stops at +4. And this is domain, so we always put the X in the middle. Now, we have to fill in our 2 inequality symbols. Your choices are either that symbol or that symbol. Look at the graph carefully. This is what the end looks like if I make it a little bigger. It's an open circle. It's not filled in. So which one of these symbols do we use when we have a not filled in circle? Yeah? The second one, exactly. So to figure out the symbol you use, look at the end of the graph. If the ends of the circles looked like this, then I would say use the first one. But this one had the empty circle, so we use the second one. All right, let's look at range. Well, first of all, range is what letter? Let's start with that. Yeah? Y. Okay, so let's put a Y. And we can even do our symbols right now. Look at the circles. They're not filled in. So we're going to use the same symbols we did before. Now, range is high and low. So if it helps you, put a line that marks how low the graph goes, and put a line that marks how high it goes. And it's going to go through every single number in between. So how low does that graph go? Yep. -3 is the lowest. And then it starts going up. -2, -2.1, -1, -0.45, -0.227. It hits every single number, starts getting into positives, and then how high does it go? And it stops. Yep. 5. Yep. So little different than listing out coordinates when it's all connected, but that's how you have to do it. Because there's just way too many coordinates to list if you started to try to list every one of them. Any question on that? I think we're at the last one. So I've told you guys a couple different names for X. I've been calling it domain. I've called it input. And I called it X. Well, there's one more term that they use. And you can use all these terms. You're not wrong. It's just certain times you might use a certain one. So another word for X is called the independent variable. And the Y, which I've been calling the range, I've also been calling it the Y. I've also called it output. Another name for that is called the dependent variable. So what we have to do when we have a word problem is a lot of times we have to figure out which letter in the word problem should be the X and which one should be the Y. You can't mix them up. So here's an example that I don't think you guys are going to write this down. We're just going to look at it and see which one makes more sense. Think about it in like real life. Let's say that I work at a job and I make $11 per hour. Would it make more sense to say how much money I make depends on how many hours I work? Or does it make more sense to say how much I work depends on how much money I make? One of those doesn't really make sense, but the other one makes a lot of sense. Yeah?
The second one would make very good sense.
The second one doesn't make sense. How much I work depends on how much I make? No. It's the other way around. How much money you make at a job, if you're paid by the hour, well, it depends on how many hours you work. So what we would say here is money is dependent on hours. Money is the dependent variable. The amount of money you make is controlled by something else. It's controlled by how many hours you work. The money depends on the hours. Money is dependent. And what letter is always the dependent? Yeah? Y. Kind of a general rule is anytime you're dealing with a problem about money, money is usually the Y value. Usually money depends on something. And then in this case, the other variable is hours. That would be the x variable, which we would call independent. So money would be the y, hours would be the x. Let's look at our last one. So we have a formula. We don't have to come up with it. They already gave it to us. You don't have to worry about why this is the formula. That's just the formula. And it says that the function y equals negative 3x plus 12 represents the amount of ounces of juice remaining in a bottle after we take x sips. So every time you take a sip, we're assuming you sip the same amount, just to keep it simple. First thing they want us to do is identify which variable is which. Well, there are two variables. The amount of liquid left in the bottle and the amount of sips you take. Based on which one is x and which one is y, let's think back. What's independent again? Is that the x or the y? Yeah. That's the x. And in which problem, what did they say the x is in this problem? Is x the ounces or is x the sips? Yeah? Sips. So the independent variable is the x, and they told us that x is the amount of sips you take. The dependent variable is the y. And what did they say that the y variable is in our problem? Yeah? Yeah, it's the ounces. To kind of put this in the terms of the last problem I did, the amount of ounces left depends on how many sips you take. The amount of liquid left in the container is dependent on how many sips you've taken. So ounces depends on sips. Ounces is dependent. So let's say we had a 12-ounce Gatorade. So we're starting with 12 ounces. And when we take a sip, we don't want to assume you could take like a third of a sip. You either take a sip or you don't take a sip. So what's the smallest amount of sips you could take? Yeah. If you had a container in front of you, and I said, tell me how many sips you want to take of it. You could choose to take, what's the smallest amount you could take? Yeah? 0. And if you took 0 sips from a 12-ounce container, what's negative 3 times 0? Yeah?
0.
And what's 0 plus 12? 12. So if you don't take any sips, you're going to have everything left. What's the next number of sips you could take? Higher than 0. Yeah? You take 1 sip. If you take 1 sip, what's negative 3 times 1? Yeah? Negative 3 plus 12. What's negative 3 plus 12? Yep, 9. So if you take 1 sip, you will only have 9 ounces left. What's another number of sips you could take? You could take, 2 sips. If you take 2 sips, what's negative 3 times 2? Yeah, negative 6. That's basically how much liquid is you've sipped out, negative 6. And what's negative 6 plus 12? Yeah, 6. Another number of sips you could take is 3. We can't take more sips than there are liquid, so we got to be careful about that. But I think you could take 3 sips. What's negative 3 times 3? Yeah,
Negative 9.
And what's negative 9 plus 12?
3.
3. Do I have a little, I still have a little bit of left, so let's try forceps. If I take forceps, plug in 4 for x. What's negative 3 times 4? What is it? Negative 12, and then plus 12.
0.
So how much do I have left now?
Nothing.
Nothing. I finished it all in 4 sips. So don't say now you could do 5 sips. No, you can't. You drank it all. You're at 0. So that's how you find the domain and the range. I think you guys will have one similar to that in the homework. If we need to go through another one tomorrow, we can do the one that's in the homework. Okay, so worksheet on 3.1, and that is on Schoology. Okay, so good job today, guys. I know there was a lot of different stuff in that one, so you guys did good. You did good.